All right, today we're going to tackle a really fundamental concept in physics, electric flux. Now, I know, it sounds a little intimidating, but it's actually a super clever idea for measuring invisible electric fields. And believe me, it leads to some incredibly powerful conclusions. So let's jump right in.
So think about it. We know electric fields are all around us, but you can't see them, you can't touch them, so how on earth do you measure one? More specifically, how could you possibly count the amount of an invisible field that's passing through some specific area? I mean, this was a huge puzzle, and it's exactly the problem that led physicists to come up with the whole idea of electric flux. And right here, you can see the problem laid out visually. You've got these red arrows, they represent our electric field, and they're streaming past this blue surface. But the real question is, how much of that field is actually punching through the surface, and not just kind of skimming past it? How do we put a number on that interaction? Well, the answer to that question is a concept called flux. It's this brilliant idea that was developed to take this invisible, untouchable field and make it something we can actually get our hands on and measure. You know, the absolute easiest way to think about this is with a great analogy. Just imagine you're standing in a river, and that flowing water is our electric field. Now picture yourself holding a hula hoop in that current. The total amount of water that's actually flowing through the hoop at any given moment, well, my friends, that's the flux. Simple as that. So if we take that idea and bring it back to physics, electric flux is really just a way of measuring how many of those electric field lines are passing through a certain area. You get more lines crossing through, that's a higher flux. Fewer lines, lower flux. It's basically just a fancy way of counting those invisible field lines. Okay, so if flux is all about counting these field lines, what actually determines how many of them pass through our surface? Well, it turns out it really boils down to two main factors, and they're actually pretty intuitive. First up is the strength of the electric field itself. In our river analogy, this is just how fast the water is flowing. A stronger river, or a stronger field with more densely packed lines, is obviously going to give you more flux. And second, the size of your surface. I mean, a bigger hula hoop is going to catch more water, right? A larger area will have more field lines passing through it. Makes perfect sense. And this image here shows you the absolute perfect scenario for getting the most flux possible. When your surface, like this red plane S1, is perfectly perpendicular to the field lines, you catch the maximum amount of flow. It's just like holding your hula hoop facing straight into the river current. That's the sweet spot. But, and this is a big but, this is where things get really interesting. See, it's not just about how strong the field is or how big the area is. There is a third, absolutely crucial ingredient that can change the entire game. Just look what happens when we tilt the surface, like S2 in this diagram. The physical size of the surface hasn't changed at all, but just because it's at an angle now, way fewer field lines are actually able to pass through it. It's like turning your hula hoop sideways in the river. All of a sudden, almost no water is flowing through it. So yeah, the orientation, the angle, is absolutely critical. So how do we possibly account for this angle with math? Well, physicists came up with a really clever trick. It's called the area vector. So instead of just thinking of area as a number, like 5 square meters, they treat it as a vector, an arrow. The length of that arrow is the size of the area, and here's the key part, its direction is always pointing straight out, perpendicular to the surface. And you can see exactly how it works here. It doesn't matter how you tilt or turn a flat surface, its area vector is always pointing straight out, at a 90-degree angle to the surface itself. This gives us a super consistent way to define the orientation of any plane we're dealing with. And this all comes together beautifully in the formula for electric flux, which we write with the Greek letter phi. It's the dot product of the electric field vector E and that area vector A we just talked about. And when you expand that, you get E times A times the cosine of theta. Now, theta is the angle between the electric field lines and our perpendicular area vector. That cosine theta part, that's the mathematical secret sauce. It's the alignment factor that perfectly handles the tilt of the surface for us. Okay, so far, we've only been talking about flat, open surfaces, like our hula hoop. But what happens if we apply this whole idea to a totally closed 3D shape, like a box or a sphere? This right here is where flux starts to get really powerful. Now, for any closed surface, there's a simple little rule, a convention that physicists all agree on. The area vector at any point on the surface always points outward, from the inside to the outside. It's a small detail, but it prevents any confusion, and it's actually the key that unlocks the whole next idea. So let's imagine a little thought experiment. We take a closed box, a cube, and we stick it right in the middle of a uniform electric field, like the one here between these two charged plates. You've got field lines going in one side and coming out the other. So what do you think the total flux through the entire box is? Let's break it down face by face. So on the top face, the field lines are leaving, and the area vector is also pointing up. They're aligned. So we get a positive flux. But now look at the bottom face. The field lines are entering it, but our area vector has to point down, outward. They're in opposite directions. This gives us a negative flux. And what about the four sides? Well, the field lines just skim right past them. They're perpendicular to the area vectors, so the flux on all those faces is just 0. So what happens when you add it all together? Something pretty amazing. The positive flux coming out the top face perfectly cancels out the negative flux going in the bottom face, which means the net, or the total, flux through the entire closed surface is a big fat 0. For every single field line that goes in one side, one has to come out the other. Now, this might just seem like a neat little math trick, but this result, that the net flux is 0, is actually incredibly profound. It really gets to the very heart of why we even care about flux in the first place. This quote from the source material just hits the nail on the head. It says, the electric flux is 0 if there are no sources of the electric field inside. The reason it all cancels out is because the things creating the field are outside our box. There's nothing inside our box creating or destroying field lines. And that right there reveals the true power of flux. Calculating the net flux is way more than just a math problem. It's a diagnostic tool. A net flux of 0 tells us there is no net charge hiding inside our surface. But if that net flux is anything other than 0, well, that's a dead giveaway. It's a telltale sign that there must be a source, an electric charge tucked away inside. Which, of course, leaves us with one final, very big question. We've seen what happens when there's no charge inside the box, but what if there is? What happens to the total flux when we actually place a charge inside that closed surface? Well, that is the doorway to an even bigger idea. And it's what we'll be covering next time. Thanks for watching.